We point telescopes at the sky and expect answers. Instead, space keeps handing us riddles that make our best theories crumble. Dark matter that outweighs everything we can see. Signals from nowhere that repeat every 11 days. Objects moving faster than physics allows. Structures so massive they shouldn't exist. These 12 discoveries didn't just surprise scientists, they broke the rules. Which ones are measurement errors, and which ones mean we're missing something fundamental about reality? If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's astrophysics data system and peer-reviewed journals in Nature. Now back to the story. Number 1. Tabby's Star, 2014 to 2017. Cygnus constellation. Astronomer Tabitha Boyajian spots a star dimming by 22% in irregular patterns. No known planet or debris disk behaves this way. The Kepler Space Telescope records brightness drops that last days or weeks, then return to normal. Citizen scientists name it KIC 8462852. The dimming events show no periodicity. Some drops block 15% of starlight, others hit 22%. The star burns at 6,500 Kelvin surface temperature. It sits 1,200 light-years away in the Swan constellation. Boyajian publishes in monthly notices, "We have never seen anything like this star." Ground-based telescopes at Las Cumbres Observatory confirm the anomaly across multiple wavelengths. Red light dims less than blue light, ruling out solid objects. Theories include comet swarms from a disrupted Oort cloud, alien megastructures harvesting stellar energy, and stellar collisions creating debris rings. None fit the data perfectly. The star brightened by 3% over 4 years of Kepler observations before the major dimming began. Infrared excess suggests circumstellar dust, but not enough to explain the dramatic light curves. The star still flickers today, watched by amateur astronomers worldwide. Cold steel mirrors, quantum silence. Number 2, fast radio bursts, 2007 discovery, Parkes Observatory. Duncan Lorimer finds a 5-millisecond pulse that released more energy than the sun produces in 3 centuries. The signal came from 3 billion light-years away and never repeated. Radio astronomers call it the Lorimer burst. The pulse arrived at 13:57 hours Universal Time on July 24, archived in survey data checking for pulsars. Dispersion measure suggested extragalactic origin. Since then, telescopes detect over 800 more. Each lasts milliseconds. Each carries the energy signature of stellar explosions compressed into radio waves. The Canadian Hydrogen Intensity Mapping Experiment finds repeating bursts from the same source in 2020. Signal FRB 181801201 repeats every 16 days for 4 days, then goes silent for 12. The pattern holds for over 500 days of observation. Peak flux density reaches 30 Janskis. Some bursts show polarization rotation, suggesting passage through magnetized plasma. No model explains the precision of the 16-day cycle. Magnetars with 11-second spin periods could explain single bursts through magnetic reconnection events. Neutron star collisions release enough energy but can't repeat. Cosmic strings snapping under tension match energy requirements. Alien beacons targeting multiple star systems remain theoretically possible. The bursts arrive faster than theories can catch them. Machine learning algorithms now detect dozens monthly in survey archives. Data points scatter. Patterns emerge. Number 3. The Great Attractor. 1976 mapping. Zone of avoidance. Astronomers notice our local group of galaxies rushing toward something at 600 kilometers per second. The Milky Way's motion relative to cosmic microwave background shows this peculiar velocity. The target lies behind our galaxy's dust plane, where optical telescopes can't penetrate. 20 degrees of sky remain hidden from direct observation. X-ray and infrared surveys reveal a massive galaxy cluster 450 million light-years away. The Norma cluster anchors it with dozens of major galaxies, but calculations show the visible matter totals only 10% of required mass, something with the gravitational pull of 10,000 trillion solar masses is dragging us across space. The entire Laniakea supercluster flows toward this region like water toward a drain. Radio telescopes mapping neutral hydrogen clouds find them streaming in the same direction at similar velocities. The motion began billions of years ago, when matter density fluctuations first seeded large-scale structure. Our destination lies in the constellation Norma, masked by interstellar dust and gas. 2-micron all-sky survey penetrates the veil with infrared light, revealing galaxy concentrations matching gravitational models. We're falling towards something we can't fully see, and the journey takes 4 billion years to complete. The cosmic flow extends across 500 million light-years. Invisible anchor, cosmic tide. Number 4, Oumuamua. October 19, 2017, interstellar space. Pan-stars. One telescope in Hawaii detects an object tumbling through the solar system at 87,000 kilometers per hour. Robert Werrick spots the streak moving against background stars. It's 400 meters long, 40 meters wide, and doesn't match any known asteroid or comet profile. The elongated shape resembles no natural object catalogued in our solar system. Light curve analysis reveals 8-hour rotation period with brightness variations exceeding factor of 10. As it rounds the Sun at perihelion distance of 37 million kilometers, Oumuamua accelerates faster than gravity alone explains. The anomalous acceleration peaks at 4 times 10 to the -6 meters per second squared. Comets exhibit similar behavior when subsurface ice sublimates into gas, creating rocket thrust. But this object shows no tail, coma, or spectroscopic evidence of outgassing. Spitzer Space Telescope infrared observations set upper limits on carbon monoxide and carbon dioxide emission. Surface composition appears rocky or metallic based on color measurements. Harvard's Avi Loeb suggests artificial origin, possibly a light sail pushed by stellar radiation. ESA calls it our first confirmed interstellar visitor. The acceleration vector points away from the Sun, consistent with radiation pressure on a low-density object, but required area-to-mass ratio exceeds natural materials. Alternative explanations include hydrogen ice sublimation, invisible to ground-based telescopes, or fractal structure creating large surface area. Oumuamua now heads toward Pegasus constellation at 11 kilometers per second, never to return. Its hyperbolic trajectory traces back to the approximate direction of bright star Vega, where it passed 25,000 years ago. Artifact or ice? The debate continues. Number 5, dark energy. 1998 supernovae surveys distant galaxies. 2 independent research teams studying Type Ia supernovae expect to find the universe's expansion slowing down under gravity's pull. Instead, Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt's High-Z Supernova Search Team discover expansion is accelerating. Distant supernovae appear 25% dimmer than predicted by decelerating models. This means space itself stretches faster over time, carrying galaxies apart with increasing force. The teams analyze 42 high redshift supernovae, ranging from redshift 0.16 to 0.97. All confirm acceleration beginning roughly 5 billion years ago. Statistical confidence exceeds 99%. Dark energy makes up 68% of the universe's energy density and acts like anti-gravity on cosmic scales. Einstein's cosmological constant lambda fits observations, but offers no physical mechanism. The energy density equals 6 times 10 to the -27 kilograms per cubic meter. Vacuum energy calculations from quantum field theory predict values 10 to the 120th power larger, the worst theoretical prediction in physics. Alternative models include quintessence fields with evolving energy density, or modifications to general relativity on cosmic scales. None explain why acceleration began recently in cosmic time. 3 physicists share the 2011 Nobel Prize for discovering something they can't explain. The Hubble constant tension between early and late universe measurements may signal new physics. Planck satellite cosmic microwave background data confirms 70% dark energy fraction. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Astrophysical Journal and Hubble Space Telescope archives. Now back to the story. Numbers scattered. Theory shattered. Number 6. The WOW signal. August 15, 1977. Big Ear Radio Observatory. Astronomer Jerry Ehman reviews computer printouts from the previous night's SETI search at Ohio State University. One sequence stands out. 6 EQUJ 5. The alphanumeric code represents signal strength climbing from background noise to 30 times normal intensity. The detection occurs at 23 hours 14 minutes Universal Time. The signal lasts exactly 72 seconds, precisely the time Big Ear's beam width takes to sweep across a point source as Earth rotates. It arrives from the direction of constellation Sagittarius, near star Tau Sagittarii, at coordinates 19 hours 25 minutes right ascension. Ehman circles the printout with red ballpoint pen and writes "WOW" in the margin. The frequency measures 1420.406 MHz, matching the 21-centimeter hydrogen emission line that SETI targets for interstellar communication. International radio regulations prohibit terrestrial broadcasting at this protected wavelength. The signal shows no Doppler drift expected from planetary rotation. Follow-up observations using the same telescope find nothing. Big Ear conducts continuous monitoring for months with negative results. The Arecibo radio telescope joins the search. Over 100 separate attempts to redetect the signal fail across multiple observatories. The signal's duration and frequency stability match expectations for transmission from a fixed celestial source. Ehman later calculates the transmitter power requirements. Assuming isotropic radiation, the source would need 2.2 gigawatts focused into space. For comparison, the Arecibo planetary radar transmits 20 megawatts. Ehman concludes, "We should have been looking every night. The source coordinates lie between star groups Chi 1 and Chi 2 Sagittarii in a region with no known radio sources." 46 years later, the signal remains unique in SETI archives. Red ink circles, cosmic question mark, number 7, Butter's Void, 1981 Galaxy Survey, Northern Sky. Harvard-Smithsonian Center for Astrophysics astronomers, mapping galaxy distributions, discover a spherical region with almost nothing inside. The void spans 330 million light-years across, larger than typical distances between galaxy clusters. Normal cosmic regions contain one galaxy per 4 cubic megaparsecs. This void averages one galaxy per 240 cubic megaparsecs. It contains fewer than 60 galaxies, where theory predicts several thousand. Astronomers call it the Great Nothing or the supervoid. The few galaxies inside show peculiar properties, inconsistent with standard formation models. Many exhibit unusually blue colors, indicating active star formation. Others display disturbed morphologies, suggesting gravitational interactions with invisible matter. Tube-shaped regions of slightly higher galaxy density thread through the void like cosmic filaments. The void's gravitational effects create detectable lensing of background galaxy images, confirming its three-dimensional structure. Statistical analysis shows probability less than 1% for such emptiness arising from random fluctuations. Cold dark matter simulations produce smaller voids with higher galaxy densities. The void formation requires density contrasts of 90%, below cosmic average in the early universe. Cosmic microwave background observations show corresponding cold spots, but not of sufficient amplitude. Alternative explanations include primordial black holes or topological defects from cosmic phase transitions. The void sits 700 million light-years from Earth in the direction of constellation Boötes. Its discovery challenges lambda CDM cosmology's predictions for large-scale structure formation. Empty darkness, cosmic wound. Number 8, phosphine on Venus, September 2020. Atmospheric detection. Jane Greaves leads an international team analyzing radio telescope data from Venus's atmosphere using the James Clerk Maxwell Telescope in Hawaii. Spectroscopic observations at 267 GHz detect phosphine gas signatures in cloud layers 60 kilometers above surface. The absorption line strength indicates 20 parts per billion concentration across the observed region. Follow-up observations with 45 telescopes of the Atacama Large Millimeter Array confirm the detection. On Earth, phosphine production requires either biological processes or extreme industrial conditions, reaching 1,000 degrees Celsius. Venus surface temperatures average 462 degrees, with crushing pressure 92 times Earth's atmospheric density. Sulfuric acid concentrations approach 100% in cloud layers, but at 60-kilometer altitude, conditions become surprisingly temperate. Temperature drops to 0 degrees Celsius. Pressure equals Earth sea level. Water vapor reaches 20 parts per million, enough for microbial metabolism. Carl Sagan speculated in 1967 that airborne microbes might inhabit these cloud layers. The phosphine signal originates from this habitable zone between 53 and 61 kilometers altitude. Photochemical models calculate phosphine destruction rates through reaction with sulfuric acid and hydroxyl radicals. Atmospheric lifetime measures just 20 minutes without continuous replenishment. Geological processes, including volcanism, lightning, and meteorite impacts, fail to produce sufficient quantities. The simplest explanation remains biological production by floating microorganisms adapted to acidic conditions. Similar acidophile bacteria thrive in Earth's most extreme environments. Venus Express and Akatsuki orbital missions detect unexplained atmospheric dynamics consistent with biological activity. Future missions, including NASA's Da Vinci probe, will directly sample cloud chemistry, acid clouds, hidden biosphere. Number 9. Gamma ray burst 080916C, March 19, 2080, 7.5 billion light-years away. NASA's Swift Gamma Ray Burst mission detects the most energetic explosion ever recorded by human instruments. The burst begins at 07 hours 12 minutes, universal time with prompt gamma ray emission lasting 63 seconds. Peak luminosity reaches 3 times 10 to the 51 ergs per second, more energy than our Sun produces in its entire 10 billion year lifetime. Ground-based telescopes, including Very Large Telescope and Keck Observatory, confirm redshift measurements of 6.7, placing the explosion when universe was just 630 million years old. The afterglow becomes visible to naked eye at magnitude 5.8, despite enormous distance, brighter than some planets in Earth's sky. No astronomical object has ever been observed at such distance without telescopic aid. The explosion releases approximately 10 to the 54 ergs total energy, equivalent to converting 6 solar masses entirely into electromagnetic radiation via Einstein's mass-energy equation. Leading models invoke massive stars over 30 solar masses collapsing into stellar mass black holes, while launching relativistic jets at 99.9% light speed. Jet collimation angles measure just 2 degrees, concentrating energy into narrow beams. Internal shock models predict complex gamma-ray temporal structure, matching observations. But total energy requirements challenge stellar collapse scenarios. The burst's gamma rays carry photon energies up to 100 billion electron volts each, approaching cosmic ray energies. Fermi Gamma Ray Space Telescope detects high-energy photons arriving 4 hours after prompt emission, indicating multiple shock acceleration zones. Optical afterglow fades according to power law, consistent with external shock in circumburst medium. Radio observations reveal jet break at 10 days post-burst. The explosion occurred in a low metallicity dwarf galaxy, typical of high redshift star formation. Modern surveys detect similar bursts monthly, suggesting these cosmic lighthouses illuminate the early universe regularly. Stellar death, cosmic lighthouse. Number 10. HD 164595's transit, 2017 detection, Kepler Space Telescope Archive. This F-type star located 2,000 light-years away in Cygnus constellation dims by up to 22% in highly irregular, asymmetric patterns spanning 800 days of observation. The dimming events show no periodicity or symmetry expected from planetary transits. Kepler mission data reveals multiple brightness dips of varying depth and duration occurring apparently at random intervals. Citizen scientists working through Planet Hunters project identify the anomaly in archived photometry data from 2011 to 2013. Professional astronomers led by Tabitha Boyajian confirm the signal represents real astrophysical variability. The star exhibits both short-term flickering on our timescales and long-term dimming events lasting weeks. Spectroscopic analysis reveals solar-type composition with slightly higher metallicity. The system shows no evidence of close binary companions or circumstellar debris from asteroid collisions. One hypothesis involves a disintegrating rocky planet continuously feeding dust clouds into the stellar system. Sublimation near the 1.4 solar radius star could create variable opacity screens. Alternative models suggest multiple planets in highly eccentric, chaotic orbits, causing irregular occultations. The transit light curves show fine structure, smaller dips nested within larger dimming events. This substructure indicates multiple objects of different sizes crossing the stellar disk simultaneously. Ground-based photometric follow-up confirms brightness variations in multiple wavelengths. The star's infrared excess suggests circumstellar dust at temperatures around 500 Kelvin. Spitzer. Space telescope observations detect variability at 3.6 and 4.5 microns. Astronomers monitoring similar stars find a handful showing comparable behavior, suggesting a new class of variable star. The mystery deepens with each observation campaign. Chaotic transits. Orbital mystery. Number 11. Cold spot. 2004. Cosmic microwave background. NASA's Wilkinson Microwave Anisotropy Probe maps temperature fluctuations in the universe's oldest detectable light, emitted when cosmos first became transparent, at age 380,000 years. Most regions vary by microkelvin amounts around the 2.7 Kelvin average temperature, but one circular area spanning 18 degrees across shows temperatures 70 microkelvin colder than surrounding regions. The cold spot sits in constellation Eridanus, at coordinates 3 hours 15 minutes right ascension, minus 19 degrees 35 minutes declination. Its angular size corresponds to 1 billion light-years diameter at the surface of last scattering. Temperature deficit exceeds 5 standard deviations from random fluctuation expectations. Inflationary cosmology predicts Gaussian random temperature variations with correlation lengths much smaller than observed. The spot's existence challenges fundamental assumptions about early universe physics. ESA's Planck satellite confirms the anomaly with improved angular resolution and frequency coverage. Polarization measurements rule out instrumental artifacts or foreground contamination from Milky Way emission. Statistical analysis across different map-making techniques consistently finds probability less than 2% for such a feature arising by chance. Some theoretical models invoke cosmic textures, topological defects in space-time fabric formed during cosmological phase transitions. These defects could imprint large-scale temperature patterns through gravitational effects. Alternative explanations include collisions between our universe and parallel bubble universes during cosmic inflation. Such collisions would create circular boundary regions with altered physics. The cold spot aligns with the Eridanus supervoid, a region of extremely low galaxy density spanning 2 billion light-years. This correlation suggests possible causal connection between cosmic web structure and primordial temperature patterns. Future cosmic microwave background missions may detect polarization signatures distinguishing between competing theoretical models. Cosmic cold, primordial scar. Number 12. Pioneer anomaly, 1980 to 2012, outer solar system. NASA's Pioneer 10 and 11 spacecraft experience unexplained deceleration as they cruise toward interstellar space beyond Neptune's orbit. Mission controllers tracking radio signals using deep space network antennas measure spacecraft positions accurate to 3 meters across distances exceeding 4 billion kilometers. Both craft slow down by 8.74 times 10 to the minus 10 meters per second squared, roughly equivalent to gravitational acceleration from a small asteroid. The effect appears constant with distance, ruling out inverse square law forces. Solar radiation pressure calculations predict acceleration in the opposite direction. Gravitational perturbations from known solar system bodies account for larger effects already corrected in trajectory modeling. The anomaly persists across multiple mission phases from Jupiter encounter through outer planet region. Thermal radiation from radioisotope thermoelectric generators creates asymmetric heating, potentially causing thrust through photon momentum. But thermal models initially fail to match observed acceleration vector. General relativistic modifications to gravity, including Mond theory, don't fit solar system data. Kuiper belt, gravitational effects remain too small by orders of magnitude. Teams at Jet Propulsion Laboratory spend decades analyzing telemetry data for systematic errors. Doppler tracking requires precise knowledge of Earth's motion through space referenced to distant quasars. Clock drifts and atmospheric effects introduce measurement uncertainties. In 2012, detailed thermal analysis finally resolves most anomalous acceleration. Heat radiated asymmetrically from spacecraft components creates tiny thrust-opposing direction of motion. Reflected infrared radiation from dish antennas and equipment bays generates net force of several nanonewtons. This thermal thrust accounts for 75% of observed anomaly. Remaining discrepancies may result from additional thermal effects or measurement systematics. The Pioneer probes now coast silently through space at 15 kilometers per second, their radio transmissions growing fainter each year as power systems decay. Final contact occurred in 2003 for Pioneer 10 and 2002 for Pioneer 11. Silent transmission, fading signal. In 2023, astronomers using the Dark Energy Survey discovered something that changes everything about cosmic void formation. The Boötes void isn't empty. It's threaded with dark matter filaments invisible to normal telescopes, forming complex scaffolding that guided galaxy formation around its edges. Weak gravitational lensing maps reveal the void's true architecture. What we called emptiness was actually cosmic engineering on unimaginable scales. The universe builds with blueprints we're just learning to read.